Yeah.
Okay. All right. So our next speaker is Thierry Stoecklin for the University of Bordeaux. Please, Thierry, the floor is yours.
Thank you. And yes, thank you to you, by the way. Thank you to the organizer to give me this opportunity to speak about this. So, fortunately, I'm speaking after a lot of people who have presented most of the field. And so I will skip a few transparencies, of course. And as mentioned by Robert this morning, I don't know where is the pointer. Oh yeah, okay. Yeah, okay. So this is part of a project that we have dedicated to three-body collisions in ionic traps. So here are the two systems that we have treated with my colleague Philippe Alvic in Bordeaux and our PhD student, who is now a postdoc, Ricardo, was dedicated to helium sodium plus and helium potassium plus. So Philippe does the QCT calculation and I do the quantum calculation. Yes, no? There was something else to put? No? Okay. So I think I can skip this transparency, you know, all these things. Effectively, I think the only thing to mention is that this project and this meeting are the result also of the progress which have been made both in experiment and theory. So the capabilities, the new capabilities of cryonic ion traps, and for the theory also the computer power which has been progressing all this year and allow to perform a very heavy calculation now. So I want to insist a bit about all the different mechanisms because we have been discussing it for already for some time, but so the process can be made either as a direct mechanism with one single collision where the three atoms or molecules give the dimer directly, and the two-step mechanism with the most famous, which is the Lindemann mechanism, which I'm considering, by the way, and the chaperone exchange, where you form first another excited dimer before getting the one you are looking for. And in the beginning, the first paper made by Smith define the three-body association rate as the summation of the four possibilities. And 10 years later, Snyder made a very important paper that many people have mentioned already, where he shows that if the set, the basis set that you use to describe one of these four channels is complete, you can obtain the three-body association rate only by treating one of the four channels. Okay, so it seems a bit contradictory, but well, it is not. And the point to keep in mind is that, in fact, the two-step and the one-step mechanism are both possible for the same system. It is not because you are treating with one mechanism or the other that the two are not possible. So here it was some non-exhaustive state of the art, but so I have mentioned some calculation. I apologize for those that I have not mentioned, and it is for theory, and so in theory the first calculation were done using statistical theory. and with so you recognize, of course, some names. And for the QCT calculation, it's relatively recent, in fact, the first calculation, when Perez-Rios and Green have developed a new general QCT theory based on 6D hyperspherical coordinates to generate the initial conditions.
Sorry, what does the Q in QCT stand for?
Quasi-classical trajectory.
Because I think ours is just classical trajectory.
No, because you do some binning. You do some binning. If you do binning, it's not anymore classical. You put in your box. You are defining. You are quantifying things. So it's a quasi-classical trajectory.
I see. Okay.
So for the quantum calculation, you have the direct mechanism and the indirect mechanisms that we have seen before. So the first calculation were done by Parker and Pack, so revised in 2014, again by Green. But they are limited to a very few simple systems because they are quite heavy calculation. And they were applied to the formation of the helium dimer. And by the way, that's an important point because the two-step mechanism is impossible, in fact, for this system because the helium dimer has only one bond state and no quasi-bond state. So if you cannot form a quasi-bond state, you cannot form the dimer using the two-step mechanism. So for the indirect mechanism, the first approximate calculation were done by Bernstein, and the first real calculation were presented yesterday by Bob for some of this system and some others. And they were based on sudden approximation, either the infinite order sudden or the centrifugal sudden approximation. So I again show you these equations that you have seen, but only because I want to insist again on for the indirect mechanism. So here you have the three-body association rate, here the complex induced dissociation one. And the hypothesis made by Bernstein back in 1969 is that you are in a local thermodynamical equilibrium. So your step one is then described by an equilibrium rate constant. And the second step is simply the relaxation rate that you obtain from close coupling calculation, atom. In our case, it's an atom-diatom calculation where you have simply included both the bond and the on-bond state of the diatom, the quasi-bond state that you have calculated. So here you recognize again the equilibrium rate constant for the first step, and here it is the relaxation process. So if you have a look at this expression, here in fact you have the translation partition function, which is proportional to t to the power 3/2, and here you have an exponential proportional also to the temperature, and here this rate coefficient. So we will see that from that we can get the temperature dependence, at least for the system we are interested in. So here, well, it is simply, I mentioned the psi equation, but you know it already, you have seen it already for the reverse process. So I want now to speak about the predicted analytical law. We have seen this morning that there are plenty of possibilities for the temperature dependence, depending on experiment or theory. So you can use the capture law for an ion-induced dipole potential, and you get t to the power minus 3/4. So it is a classical approach, classical treatment of translation. And one has reduced the problem to the only long-range potential. So this result was obtained using the two-step mechanism, in fact, by Smirnov in 1967. But when he did that, he didn't use an equilibrium rate for the first step. So this is the reason why he obtained the same temperature dependence. And Perez, Rios, and Green obtained the good temperature dependence also in t to the power minus 3/4, as was obtained by Smirnov, but of course with a different factor for the rate. And it compares well with QCT, for example, for this system. I've mentioned only this system, but you have seen these last days that it works also very well for other systems. So now for the experiment, we have seen that we can obtain t to the power minus 1, t to the power minus 0 rate this morning. So what about the prediction of the two-step mechanism and the equilibrium rate constant? So capture theory applied to the second step of the process give a t to the power 0 because we have a charge-induced dipole potential. So if we replace t to the power 0 in this expression for the second step rate coefficient, and we see that we have still the t to the power minus 3/2, so we obtain t to the power minus 3/2 instead of the t to the power minus 3/4 obtained using the direct mechanism. So what I want now to show is that if we have performed, in fact, the relaxation close coupling cross-section using an L2 basis set, both for the bond and the quasi-bond state, in order to preserve the S matrix unitarity. And after that, we need to include a continuum normalization, and the continuum normalization, which was not in the expression that you have seen before. So we are not using the Sturmian approach of Bob. So we need to include this normalization factor, which is proportional to e to the power minus 1/4. So if we do that, and now we can mimic the one-step mechanism using the two-step formulation by replacing the summation by an integral over the energy. So and if we do that and use this normalization factor, which is proportional to e to the power minus 4, we obtain the good temperature dependence, exactly the one that was obtained for the one-step mechanism. This means that, in fact, it is a discretization of the continuum which gives the difference in the step one and two, in the one-step and two-step temperature dependence approach. If we have now a look at the Wigner law, so the one-step approach was used again by the same team to obtain again a t to the power minus 3/4.
I don't understand
No?
what you mean by that. It's a constant, energy-independent constant of the three-body rate in the quantum limit. This is a pure quantum treatment, and it's not minus 3/4.
It's t. Sorry, so I need to correct it. So it is t constant.
Yeah.
Okay.
And
Sorry.
in the zero energy limit. Yeah.
Okay, I'm sorry. I'm sorry. That's a typo. That's a typo. Sorry. Okay, t constant. Okay, and if we use the two-step mechanism, the exponential term cancel to zero the TBA rate, which means that now we have not t to the power constant, but we have t to exponential, an exponential, which is different, by the way. So this is not a failure of the steady state approximation because, as you know, the steady state approximation is not valid in the limit of vanishing temperature, but it's simply the fact that the S wave, which is the case of the Wigner regime, cannot produce a quasi-bond state because we don't have a barrier. If L is equal to 0, you don't have a barrier, you cannot form a quasi-bond state. That's very simple. So in this case, a one-step mechanism only is possible in the Wigner regime. That's what it should mean, I think. But we can discuss it. Now for the PES calculation, so we have, so this is again the result of the calculation of Philippe. So we have the summation of the three terms that was also presented before. But we have also this three-body term, which is neglected for a van der Waals system. So for a van der Waals system, you can neglect it and have only the summation of these three terms. So in our case, for the helium-helium diatom, so we use a potential made by Aziz. For helium Na+, it is, so you have the detail of the calculation, and for helium K+ as well. And also we have the good variation as a function of R of the diatomic potential. So this is the result for the atom-diatom case, for the collision of helium with helium Na+. So you see that the well depth is relatively shallow, 340 centimeters minus 1. It is a van der Waals system, and it is also a band system. So here it is, we need also to calculate the bond and the quasi-bond state. So for the you see that the dissociation energy of the diatom is very close to, in fact, the energy of the triatom. It's a relatively large rotational constant. And we use a stabilization method to calculate the quasi-bond state. And we obtain 67 bond state and 13 quasi-bond state. So I will not give more detail about the stabilization methods that you know, most of you, I suppose. But I will simply say that we have also used atom-atom calculation, elastic calculation, and we obtain the resonance exactly at the position of the energy given by the stabilization method. And what is more important is that, in fact, we use a special propagator, which is a Magnus propagator, which has a nice property, which is that you can calculate analytically the wave function that you propagate inside each interval, and then you propagate an analytical derivative of the S matrix. You don't need to use a numerical derivative of the S matrix, which is usually not very accurate. So, and with that, you obtain the Smith lifetime matrix, and then you diagonalize it, and you obtain the resonance lifetime. So it's very simple to identify the position of the resonance, because you look only at the maximum of the Smith lifetime eigenvalues, and you get at the same time the energy position and the lifetime. So here are the results for helium Na+. So you see here are the bond states, so with a maximum value of capital J equal 21 and 7 vibrational states at the most. And here the quasi-bond state. And you see here the result, so the energy obtained with the stabilization method and the energy obtained from the elastic collision. So you see that it is very similar. And here the eigenvalue of the Smith lifetime matrix in picoseconds. So now we may have a look at the relaxation rates obtained by the collision with helium. And you see that effectively the Langevin formula is not a bad approximation, at least between 1 and 300K, because it's almost constant, because as it should be for a charge-induced dipole. And it is a near-resonant energy transfer mechanism. So why do I say that? Because, in fact, you obtain the largest rate coefficient with the lowest delta E between the quasi-bond state and the accessible bond state. An also interesting point is that if you compare this sorting of the rate coefficient with the lifetime that we have obtained in the previous step, which is an approximation which was used in the past in the first paper when it was not really possible to calculate this lifetime, you will see that there are many exceptions that it doesn't work well. So it's not a good approximation to use the lifetime to sort the magnitude of the two-body rate coefficients, relaxation rates. So now this is the result for the three-body association rates, where here you have the QCT calculation and here the summation over all the contribution of the different quasi-bond states that we have obtained. And you see that so the QCT follows the T to the power minus 3/4, and the two steps follow the T to the power minus 3/2, which is what we expected. The best agreement between the QCT and the quantum calculations is between 10 and 100 Kelvin. And what is also important is that you see that the very low temperature is described, but also by the quasi-bond state of the lowest energy. That means that you need to be sure that you have calculated properly the lowest quasi-bond state energies. Here, the same result for helium with potassium plus. And here, the dissociation energy is around 200 centimeter minus 1, so it is shallower than for helium Na plus. It is also a bent geometry. Here again, we have also a dissociation energy for the diatomic potential, which is comparable. And we obtain a few less bond states than for helium Na plus, only 54 and 9 quasi-bond states. So here are the bond states that we have obtained. And here the quasi-bond state, and again with the lifetimes that we have obtained from elastic calculation. And for example, this energy was obtained only from elastic collisions. So from elastic collision, you see here, for example, so that the L equal to resonance that we have taken here as a quasi-bond state, and that we have included in our calculations. So now that's the final result for the three-body association for helium K+. So you see that the agreement with the QCT calculation and the two-body, the two-step quantum calculation is okay. And but if we miss this low energy, of course, well, the agreement will be not as good at low temperature. But anyway, below 0.1 Kelvin, one cannot expect that a classical method can work. So it's not really a good criteria. So I can now conclude this study. So I think we have seen that elastic atom scattering calculation are a useful tool to complement the stabilization method for finding the quasi-bond state and lifetime. The maximum of the quasi-bond state selected rate coefficient decrease monotonously as a function of their energy as a result of the decrease of the two-body relaxation rate as a function of also the energy of the quasi-bond state. The predicted rate is around 10 minus 29 at 10K, and the global agreement between quantum and QCT approaches is obtained between 1 and 300K. Again, we have seen this temperature dependence, and we propose that this difference results from discretization of the continuum, and also that the one-step mechanism is only possible in the Wigner regime. And I would like to conclude with that, and I think that the information about the dominant direct or indirect mechanism within a given temperature range can be inferred from the temperature dependence of experimental results by comparison, but probably in the future we will be able also to predict that more easily, I hope. Thank you for your attention.
Yeah, so can you explain what you mean by the difference in the temperature dependence results for the discretization of the continuum? I'm trying to understand.
Okay, so that's very simple. In fact, yeah. So that's here.
So let me ask you, are those U's just quasi-bound U's?
Sorry?
The U's in your notation, do they include the direct non-resonant contribution, or are they just the resonant contribution?
No. I included only the resonant, the quasi-bond state to perform my calculation of the rate coefficient.
Okay, these U's in the summation are not including any of the non-resonant.
No, that's here that they are included. What I mean is that we can mimic the one-step mechanism using the two-step mechanism only by replacing the summation by an integral, and now including all the resonant states. Okay? And if you do that, if you do the integral of that, you obtain kt to the power 3/4, so you divide by it, and you obtain kt to the power minus 3/4. So, well, it's possibly only a coincidence, but
Yeah, well, the unbound states.
sorry?
You know, that sum that you had previously is a discrete sum.
No, but
You're just adding
yes.
resonances, but
Yeah.
you also should be including the continuum, which is what you're doing now.
Yes. Yeah, it is there.
And so you're saying that this step here is what's determining the temperature.
Exactly. That's only because we have done the calculation over quasi-bond state only.
One thing that's a little confusing is your mention of our quantum calculation, because everything else in your whole talk was classical.
Yeah.
So that a little bit confuses me, but.
Yeah, sorry about this typo.
No, that's fine, but I should mention that, like, for different symmetries, that t to the 0 is different. Like if you have spin polarized fermions.
Of course.
then you have
No.
a different, threshold law.
Yeah. I'm speaking only about this special case where we are speaking about 3 atoms, and one of the atoms is an ion. That's it. I'm not speaking about all the systems.
But even if it was an ion and 2 fermions,
Yeah.
it would not. Then the t to the 0 would change.
Of course. So yeah, I agree.
Just wanted to point that out.
Okay.
Everything else in your talk was classical, but that one line.
Yeah. I'm sorry, I correct it. Well, or you remove it. Yeah. Okay.